All right, so we want to show that if E and F are independent, then the complement of E and the complement of F are independent. Okay, so we're going to start by assuming the hypothesis. We're going to assume that E and F are independent. Suppose E and F are independent, which means that the probability of E intersect F is equal to the probability of E times the probability of F. We must show that the probability of E complement union intersection F complement is equal to the probability of E complement times probability F complement. Okay? All right. So I think I'm going to start with this side, and I'm going to play with it until it hopefully turns into this. All right? So probability of E complement times probability F complement. I'm going to write that in terms of probability E and probability F. Now, what does probability E complement have to do with probability of E? What do they add up to? You remember? They add up to 1. Which means I can replace probability E complement with 1 minus probability E. And I can do the same thing with probability F complement. Oh my gosh, it's not that funny. Okay, so now I'm going to multiply that together. FOIL, 1 minus probability E minus probability F plus probability E times probability F. So far, so good? Okay, now we know that probability E times probability F is the same thing as probability E intersect F, because we know that E and F are independent. Okay. Well, let me point out something to you, because all the time while I'm doing this, I'm keeping in mind that I'm trying to get to this. I'm trying to get to that. All right. So here's what I'm going to do. And I'm also keeping in mind that I know another form for this. You remember something called De Morgan's Law? And it said that E complement intersect F complement is the exact same thing as E union F complement over the whole thing. That's called De Morgan's Law. Okay? So when I think about that, I'm noticing that this here looks kind of, sort of, vaguely familiar. Except the signs look kind of funny. If you pull a minus sign out of all of those, you get probability E plus probability F minus probability E intersect F. And now that is exactly the same thing as, what is that? The probability of what? That's E union F. That's the inclusion-exclusion formula, right? We're almost there. Okay. So all that stuff in the parentheses is probability E union F. And 1 minus probability E union F is the same thing as probability E union F. What? It's the complement. It's using that complement rule again. Oh boy. That's exactly the same thing as this. What we're trying to show that's equal to. Woohoo! Okay. So we just showed that probability E complement times probability F complement is the same thing as the probability of the intersection. And that is exactly what it means for E complement and F complement to be independent. So that's how you prove something like that. And I think that once I post the homework for this section, which I haven't done yet, I think that there is a homework problem that's kind of similar, except that it might ask you if E and F are independent, show that E complement and F are independent or something like that. In other words, only one of these has to be complement, and it still works. Okay? All right, so if you use this example as a model, you should be able to work that out. All right, now we come to the fun part. This is a really famous probability question with a kind of surprising answer. I need to double check something. Did we lose anybody during the break? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We lost one person. All right. Okay. Well. Okay. So here's the question. How many people need to be in a room, and I'm going to say this a couple different ways, so that the probability that at least 2 of them have the same birthday is greater than 1/2? In other words, suppose that I asked you, are you willing to bet money? Pretend you don't know anything about anybody in this room. I know you have some friends in here. You might know when their birthdays are. Pretend you don't know that. You're in a room with a bunch of strangers. And somebody asks you, are you willing to bet money that there are at least 2 people in this room that have the same birthday? All right. Okay. So how many people would need to be in the room for you to be comfortable taking that bet? 367? You're not terribly adventurous, are you? Well, I don't think you're going to get very good payout on that bet. Right? Okay, so yes, I agree. If there are 367 people in the room, that's a safe bet. By the what principle? That's the pigeonhole principle. If you have 367 people, you must have 2 that have the same birthday. Even if there's one that's February 29th, he's being extra careful. Oh, it'll be, in that case, when there's 367 people, it's probability 1. It's guaranteed. Guaranteed, right? Okay, so yes, we would all take that bet if there were 367 people in the room. Would you take the bet if there were 2 people in the room? Probably not. Okay. So where is the cutoff? At what point between 2 and 367 are you more likely than not to win? 200? I'll write down some guesses. 200. 20? Okay. 183. Somebody always guesses 183 because that's half of 366, right? All right. Well, okay. So we're actually going to find out. So if I leave if I leave myself out of it, do you want to play? Yeah. Okay. So 20 people. 20 people. So we're going to see if this person was right. All right. I personally, but it's not fair because I know what the answer is. I would not bet with 20 people in the room that there are 2 people that have the same birthday, but I also won't be surprised if there are. All right. So let's see if there are. I don't have, by the way, very good luck with this. I know what the math says, and sometimes I just have bad luck. Okay. So my guess is that everybody, all 20 of you, have different birthdays. And so the easiest way to do this is raise your hand if you have a birthday in January. Okay. What day? The 4th and the 7th. Okay. So far I'm okay. February? 2 people in February. What day? 26th? 11th. Okay. March? 1 person. Okay. What day? 11th. All right. We knew we were okay on March. April. Who has a birthday this month? Only 1 person. Is it today? Oh, it's coming up in a couple days. Happy birthday. All right. May. Who's May? We have 2 May people. What day? 27. 31st? Okay. So far I'm okay. June? Any June? Only 1 June. What day? 22nd. Okay. July? 2 people in July. All right. I'm feeling good. August? Oh, 3 people in August. I'm feeling nervous. 9th, okay. September, that was close. What day is your birthday? 20th? 24th, kind of close. October? 1 October, what day? The 8th, okay. November? 2 people in November? 22nd? 15th? December? Oh, I won! What day? 4th. Okay. This is really interesting, okay? Because it turns out that the answer... No, it's even more interesting than usual. So, all 20 of you have different birthdays, which is what I would have predicted. Here's how you figure it out. Instead of looking at the probability that 2 people have the same birthday, you look at the complementary event. All right, which is that everybody has a different birthday. Okay. So I'll show you how to set this up. Okay. All right. So if you have 1 person, it's not really interesting, is it? Okay. If you have 1 person, the probability that that person's birthday will not be repeated is 1, right? And the way that you figure that out is, okay, so with 1 person, there are 360. Oh, and by the way, I'm sorry. Nobody was February 29th, right? It's easier if you just ignore February 29th. Just makes it easier. So leaving February 29th out of it, there are 365 different birthdays, and this person can have any one of them, any one of the 365. So we're safe if there's only 1 person. If there are 2 people, well, now there's a chance of it happening. you look at the number of combinations of birthdays. So the first person can have any one of 365 birthdays, and the second person can have any one of 365. That's your sample space. In order for the birthdays to be different, the first person can have any birthday, and the second person can have any birthday except for the first person's, right? So you're down to 364 choices. Okay, and that comes out to be some still pretty big number. I want to say it's something like 0.997. All right. If you have 3 people, then there are tons and tons of different ways for those 3 people to have their birthdays. The number of ways where all 3 of them are different is first person can have any birthday, second person can have any birthday that's different from the first one, third person has to have one that's different from the first 2, right? And that brings it down to something like 0.992. Okay. So then what we're really interested in is the complement, the probability that at least 2 are the same. All right, so when you have one person, that's not going to happen. When you have 2 people, there is a 3 in 1,000 chance that that'll happen. And then there's about an 8 in 1,000 chance it'll happen with 3 people. So we want to know when is the first time that this number goes up above 0.5. All right, so you're about to see why I bet the way I bet, but at the same time I wasn't terribly confident about my bet. And that's because the first time that the probability at least 2 people have the same birthday goes above 0.5 is when you have 23 people. 23 people, it is more likely than not that 2 people will have the same birthday. Okay? So it worked out. The reason I said I wasn't having great luck with it lately, I don't remember what happened in this class last year, but I remember that a year and a half ago, I was teaching 2 finite math classes at Stanislaus, and I lost in both classes. In one class, it was over 23. It was like almost 30, and I bet at least 2 of you have the same birthday, and they didn't. All right, and then the second class was under 23, and there were 2 that did have the same birthday. So I lost twice in a row. But the reason I was laughing even more just this time, you said your birthday is May 31st. If I had included myself and been person number 21, we would have had a match. And that's almost exactly what happened the very first time I ever did this. I will never forget this as long as I live. There were 22 students in my class, 22. They all had different birthdays. But one of them was May 31st. And so if I had included myself and been person number 23, it would have worked exactly like this predicts. It predicts it doesn't work with 22. It predicts it does work with 23. So in our case, it didn't work with 20, but it would have worked with 21. All right. All right. So most people are very surprised when they hear it only takes 23 people. All right, because like I said, 183, that's a very popular guess. 20 was very close. Whoever said 20. Okay. All right. And that is all I have for 7.2. So now I will put up some homework. I'll probably do it as soon as we're done. I'll just steal it off last year's Blackboard. Oh, what I was about to tell you is that since we're getting so close to the end, just wild guess off the top of my head, we might have our 3rd exam. Let me think about dates here. Something like, the latest we'll have it is May 12th. That's the latest we'll have it. And that's in, what, 3 weeks? All right. So I am just going to wait to collect the next homework. I'm not going to do it one time before the exam and then return that and then do it again at the exam. I'm just going to collect it at the exam. All right. So it's up to you to, check your answers in the back. All right, try to do the problems without looking at the answer, and then check your answer. And I'll just collect everything at the exam. It's coming up too quick. I won't be able to turn it around that fast. There's not a firm date. All I said was the latest it'll happen is May 12th. I'm going to have to talk to Professor Kanemoto about the final project and how much class time is needed to work on that. It might even come a little earlier. All right. May 12th gives us would give you the last week of regular classes up until, and I think we usually make the final project due like on what would normally be our final exam day. All right, so it might even be a little earlier. I'm just looking at this and I'm noticing the next few things that I have prepared are 8.1 and 8.2. I'm thinking about skipping 8.2 this year. 8.1 is a lot more important. And then we get into chapter 10. And I don't exactly understand why this is set up the way it is, where there's some sections that are together. But anyway, I'll look through that and figure out how much of that we can cover. Hopefully all of it. All right, let's just start looking at 8.1 just to see what it's about. Maybe I have time to introduce it, and then we'll actually get into it on Thursday. No, today's Thursday. On Tuesday, I guess. All right, so I did put up these notes a little while ago before class. Okay, so a little bit of advanced counting techniques. So you remember we did a little bit of stuff with recursive functions. And so what we're going to do now, and most of the stuff we did with those was pretty simple. It was just, okay, here's the recursive definition. Tell me what are the first few terms. And gave you a little extra credit for doing that on Maple at the last exam. And then going the other way, can you come, or wait. Okay. Anyway, that was just really basic stuff. So what this is actually finding recursive formulas to use on word problems. Okay? And that's kind of challenging. All right? A couple of famous examples that I'm going to talk about today, and then I don't know how much else we'll get through. So recursive definition of a sequence specifies one or more initial terms, your initial conditions, and a rule for determining subsequent terms from those that precede them. Okay? A rule of the latter sort is called a recurrence relation. So this rule here, the rule for determining subsequent terms from those that precede them, is called a recurrence relation. And a sequence is called a solution of the recurrence relation if its terms satisfy the recurrence relation. Okay, so a couple of famous examples. Fibonacci. Talked about Fibonacci a little bit, but I didn't really tell you where it came from. All right, so this problem was originally posed by, I've heard this guy go by a bunch of different names. Leonardo Pisano, also known as Fibonacci, goes back to the 13th century, and it talks about a formula for predicting how many rabbits are there going to be after a certain number of months have gone by. Okay, so this is using a few kind of unrealistic assumptions. All right, so you have a young pair of rabbits placed on an island. Rabbits start breeding when they are 2 months old, according to this. And then after they're 2 months old, they each produce a pair of rabbits every month. All right? And so the recurrence relation that we're looking for is how many pairs of rabbits are on the island after n months. So here's one of the unrealistic assumptions. All right? Okay. So here is the first pair of rabbits that was placed on the island. So they've got them sorted into young pairs. So the young pairs don't reproduce. And then these are the reproducing pairs. How many reproducing pairs? So at the beginning, one young pair was placed on the island, 1 month, so they're not ready to reproduce yet. and then that pair is still there in month number 2. All right. At the end of month number 2, this pair is going to reproduce. So these rabbits, let me roll this up because I want to show you. I kind of wish this was color-coded so you can keep track of which rabbits are which. At the beginning of month number 3, this pair moves over here because now they're old enough to reproduce. And here is the pair of rabbits that they just gave birth to. All right, so now you have the one reproducing pair and the one young pair. Okay. So in the first month there was one pair. Sorry, you can't really see that. And in the second month there was one pair. And now in the third month there's 2 pairs. Okay. All right, so at the beginning of month number 4, this pair is still here. That's the same pair. And they give birth to another pair. All right, so now you have two young pairs. This pair is now 1 month old, and this pair is newborn. So at the beginning of the next month, this pair is going to move over here. And the original rabbits are going to have a pair of new rabbits. This pair that just turned 2 months old is going to have a pair. All right. And there's one other young pair. This pair is still too young to reproduce. Okay. And so you can see that the total pairs of rabbits fit. We talked about the Fibonacci sequence before. It's where you get each term of the sequence just by adding the last 2. All right, whatever the last 2 numbers are, you add them together, and that's how you get the new one. So the reason that that works for the reproducing rabbits is, okay, so F sub n is the number of pairs of rabbits after n months. Okay, so at the end of the first month, the number of pairs of rabbits is 1. And because that pair doesn't breed during the second month, F sub 2 is also 1. To find the number of pairs after n months, you add the number on the island the previous month, because those rabbits are still there. All right? And the number of newborn pairs, because the rabbits that were there 2 months ago are all reproducing. So this F sub 2 represents new rabbits, brand new, just born. And the F sub n minus 1 is how many there were last month. Okay? And so F sub n is equal to F sub n minus 1 plus F sub n minus 2. And your initial conditions are that F1 and F2 are both equal to 1. So, seen that before. I showed it to you well back when we first talked about recursive definitions. That's the Fibonacci sequence. All right, and that's where it originally comes from. And it comes up a whole bunch of other places in nature. It's actually really cool. It's worth a little excursion on Google sometime when you're, I don't know if anybody else does that. You're sitting there bored and you think of a whole bunch of things you're curious about. It's really nice having Google. I don't remember what we did in the days when we used to wonder stuff and couldn't look it up right away. We just didn't know. All right. So that's your Fibonacci sequence. And I think I have time to tell you about one more thing, and then we can really get into this on Tuesday. Towers of Hanoi. That's another fun one. Towers of Hanoi is a puzzle. And the rules of the puzzle are you have to move that pile of discs onto a different peg. And there are 2 rules. You're only allowed to move 1 disc at a time. And you're never allowed to put a larger disc on top of a smaller disc. Okay? And so there's a recurrence relation that talks about how many moves does it take to get, to move all n disks. Okay? There's a recurrence relation for that. So you start, okay, so here's the background. It was invented by a guy named Lucas, Edouard Lucas. And so those are the rules that I kind of just described. Never place a disk on top of a smaller disk and move one disk at a time. Okay? So here's how you can figure out a recurrence relation for how many disks or how many moves it takes to move the whole pile. So start with the initial condition. All right, or actually we're going to do that at the end. All right. So if you start with n disks on peg number 1, you can transfer the top n minus 1 disks to peg number 3, say, using this many moves. All right. Okay. And then, let me kind of keep track of this over here. So here is your game board. My picture's not going to be as nice as, I'll just do it like that. All right. So you start by moving all the disks except the bottom one to peg number 3. Could be number 2. It really doesn't matter. The number of moves that takes is h sub n minus 1. All right. Then you move the largest disk to peg number 2. How many moves does that take? 1. Right? And then move n minus 1 disks to peg number 3. And then you move those same n minus 1 disks that are now on peg number 3, you move them to peg number 2. Move n minus 1 disks from peg 3 to peg 2. And that also takes h sub n minus 1 moves. Okay? So the relationship between h sub n and h sub n minus 1 is that h sub n is equal to 2 times h sub n minus 1 plus 1. And the initial condition is that, all right, how many moves does it take to play the game if there's only one disk? Just one. Move that one disk from peg 1 to peg 2. You're all done. Okay. All right. Here's something kind of fun. I think I'm going to do this instead of showing you the next thing. I'll save that for next time. Where is... You guys all use Excel, right? Okay. So I'm going to start with a 1 up here. Here, let me make this bigger. Just get a rough idea. All right. And now... actually, let's do it like this. Insert row. Okay. All right, so we know that takes 1 move. And then... I'm not going to use this for anything other than just labels. All right, so watch what I'm going to type in here. I'm going to say that this is equal to 2 times the number in the previous cell plus 1. All right, so it takes 3 moves to do the puzzle with 2 discs. You can picture that, right? Move the small disc to peg 3, move the large disc to peg 2, and then move the small disc on top onto peg 2, right? 3 moves. And then if you copy and paste this all the way down, you see that it blows up pretty fast. Okay, and you might even be able to see those numbers might look kind of familiar. I bet they look even more familiar to you than they do to, you know, people that are in a different major, maybe. All right. But anyway, let's leave that there, and then the next time we'll look at how to solve that. It turns out this recurrence relation is actually not too hard to solve. All right. Okay, so look for 7.2 homework. I'll put it up. I'll try to put it up. Actually, I'll just put it up now.